welcome everyone. So as David was saying, this is the first technical talk in what we hope is a series of informative technical talks. The hope is that we give at least one technical talk every month on an area that is of interest to the lab as a whole. So I thought that today we would kick off with what is potentially a very controversial topic, and that's ROS1 versus ROS2. So the way that this talk is going to go is I'm going to start by talking about and providing a short tutorial on ROS1, just so everyone understands and is on the same page, because I know only some people in the lab actively use ROS. And then we'll look at ROS2 and the differences between the two of them. Oh, that's the wrong keyboard, that's why. Okay, so ROS is a middleware that facilitates communications between multiple processes on a robot. So it allows you to create distributed systems. And the benefit of that is that it introduces fault tolerance into your robot. So for instance, if one of your processes crashes, the other processes hopefully can either detect the crash and recover, or you can bring that back up without having to start up a whole monolithic system. It comes with a variety of tools for debugging and introspection, which makes it really, really handy when you're trying to do things very rapidly. There's a lot of tools there to help you do things. And one of the biggest benefits of ROS, and why ROS is so ubiquitous in the robotics community, is it has a massive community behind it. So there are other people trying to make ROS contenders, but they always kind of fizzle out because they just simply don't have the inertia that ROS has in the community. So there's hundreds of packages that cover lots of different things. Some of them are created by commercial manufacturers, such as Intel for their RealSense cameras, and some of them are just from robotics researchers such as us. It's also platform and language agnostic, and it's designed to abstract away differences in hardware. So as far as ROS is concerned, a RealSense and a Z camera look effectively the same once you've abstracted it away in ROS. Wrong computer again. So fundamentally, there's two main languages that are used for development with ROS. That's C++ and Python. So in ROS1, the main language for Python is Python 2.7. And there is a lot of overlap between the two APIs for these languages because they are developed independently of each other. There's not a shared library that they build on top of. But this does introduce some infuriating differences between the two, such as the fact that Python is inherently multi-threaded when you implement your subscribers, which I'll talk about later, whereas C++ is all done in a single thread. And so there's weird differences like that that make swapping between languages somewhat disconcerting. How ROS is structured. So in ROS, we refer to this thing as the ROS node graph. So your system in ROS is basically a collection of nodes connected by vertices, and your nodes are basically synonymous with the word with processes. So in ROS, each process that's involved in the ROS graph has a single node attached to it, and each process can only have one node. So a lot of the time when people talk about ROS and they say start this node, basically means launch this process or this executable or something like that. Each node is generally responsible for a single task. So I have one node that is responsible for getting camera images from my camera, and then I have another node that takes those camera images and computes detections on them. There are different ways, there are three different ways that you can have nodes communicate. The first is publishers, subscribers, which we'll talk about, services, and action servers. And in ROS1, action servers are a bit of a fudge because they were kind of a weird afterthought. So they're actually not in the core ROS library. They have a secondary library just for action servers. And each communication mechanism utilizes associated message types, which you compile. And these include things like string messages, pose messages, and image messages. So a ROS graph would look something like this. where each of the nodes is an individual process, and the wires connecting them are topics that are communicating unidirectionally. Some of these nodes, such as the CCG node off in the top corner there, is a service node which doesn't maintain active connections. So that's why it's not connected at the moment to anything. By the way, if anyone has any questions, please feel free to pop in. I don't want this to be completely one way. So what I'm going to do now is I'm going to talk about the 3 communication mechanisms in ROS and what they are and what they're used for. As well, I'm going to provide some demonstrations and look at some code for them. So the first one we're going to look at is publishers and subscribers. So publishers are unidirectional broadcasters. So what this means is I create a node, I designate it as a publisher, and it starts shouting into the ether. And at the other end, hopefully, I might have a subscriber that would hear that message. Now, publishers are one-to-many, which means I can have many subscribers that are listening to the same topic, and that message will, when it comes out of my publisher, get broadcasted to all of the various publishers. You can also have no subscribers active at a time, and the publisher will continue to publish, but under the hood, it doesn't really do anything. Subscribers are unidirectional listeners, so they will listen for incoming topics that they're interested in, and they are many to one. So they can listen to a topic that is being published by multiple different nodes. So in this case, nodes 1, 2, and 3 are all publishing on the same topic, and node 4, the subscriber, is listening to all 3 of those. So what I'll do quickly is I'm just going to pull up a demonstration. If anyone has any questions, please ask. So the first thing I'm going to do, I'm going to show you how this works. I'm going to show the executables running, and then we'll just have a quick look at the code. So what will happen here is I'm going to run my publisher node. I've called it Talker, and at the moment it's trying to connect to this thing called the ROS master, which we'll talk about a bit later. And until it can connect to that master, it really can't do anything. So I'm just going to start up a ROS master over here. Now, my publishing node is basically spitting messages out into the ether. It's sending hello messages, but there's no one to actually receive them. So what I'll do is over here, I'm going to start my listener node. And every time it receives a message from my publisher, it's going to print the message that was sent, which is just howdy partner. Like I said, you can have multiple listeners on a single topic. So I can start up using this ROS topic echo, a bespoke subscriber. And you can see I now have 2 nodes that are listening on the same topic. Now, the code for this is very straightforward. This is all the code that is needed for a publisher and subscriber. So, oh, it's really disconcerting looking at that there. Okay, so the main thing we do with a, when we're creating, I'm going to do all this in Python, by the way, just because doing it in C++ adds way more complexity than I'm willing to deal with for this talk. But the main thing with ROS is I have this fundamental import here called ROS_PY, and I also have things called messages that I can import. So for instance, I talked earlier about the string message, and then I have my simple main function. So the first thing I have to do is I have to initialize my node. And like I said, you can only have 1 node per process. So under the hood, it's effectively a singleton. Once I've initialized my node, I can then create a publisher. I give it a topic name, the message type, and then the size of the queue. And then until I hit Control-C, basically I'm just going to start publishing at a rate of 1 Hertz, just this message, howdy partner. All right, it's very, very straightforward. Don't look there. All right, my listener, my subscriber, the same thing, import ROS_PY. It's also using this message type called string. I have a callback, which we'll come back to. But again, the same thing, I have to initialize my node. I've given it a name called listener node. I create a subscriber, And you'll notice that the subscriber and the listener both have to share the same topic in order to be able to find each other. Right? It has a string message type, and it takes in a callback. Now, the callback is basically invoked every time the subscriber receives a new message. And one of the weird things I was talking about earlier between C++ and Python is that in C++, this subscriber effectively gets spun off into its own thread, whereas in C++, you actively have to check for new messages using this spin function, which in Python is basically just a while true keep running loop. It's a bit of a waste of time. It's very confusing if you're just trying to jump from one to the other, however. Okay. So the next thing, so we have this idea of just a publisher and subscriber. The publishers don't actually know or care if anyone's listening. The subscribers listen, but they don't tell the publisher that they have received messages, etc. It's all kind of a bit wishy-washy. So the next thing we have is this thing called a service. And services enable request-response type messaging. So with a service, I can have, I shouldn't say publisher subscriber, let's ignore that, but my node 1 can send a request to node 2 asking it a question, like, what is 5 plus 9? And node 2 can do some processing on that while node 1 is waiting and send back an answer. So I send a request, I get an answer back. Services are blocking and they can't be cancelled. So if you have time-critical software, services are actually dangerous. Right, so just a quick example of services. It's very much the same as publisher subscribers, which makes this a lot quicker. What is this? This is ROS1. Excellent. ROS1, ROS1, my services, my service. Right. So over on the left here, I have a service. On the left, I will ROS run my what's called a client. So this is the node that will connect to my service and ask it a question. So all this is doing at the moment is just sending alternating true-false messages. And you can see over on the left that it's being printed out, and over on the right. So my service on the left is printing what it's received from the client. It's then sending back the exact same value in the success field of my response. And there's also a message field, which I've just filled in with information. You can create your own bespoke messages, by the way. So there's a lot of flexibility in what you can do with these things. So for instance, you can create services where you pass an image to your service and the response back might be a set of detections for that image. Right.
So Gavin?
Yes?
Is there a general rule of thumb as to when you would use a service over a publish-subscribe system?
Yeah, so you would generally use services in a situation where you want the answer to correspond to the input. So if I publish an image and I get back detections, but I'm still publishing images while it's processing the first image, it's hard to tell which image corresponds to which set of detections. Whereas with a service, I can send my image and I know that the response I get back is the set of detections corresponding to the input image. Does that make sense?
Okay, so best used in instances where you do want to sort of set things on pause for a moment while you deal with information.
Yes.
Okay, cool.
Okay, and the last thing in ROS is this concept of an action server. Action servers in ROS1 are kind of a hacky on top of publisher subscriber type thing, but effectively they use a state machine model and publishers and subscribers to track long running tasks. So what I can do with an action server is I can send a goal and it will give me feedback while it's running the task associated with my goal. And then when it concludes, I get back a result saying I'm done and here's the result of my action. So a situation where you might use something like this is if I have a robot in the meeting room with Toby and I want to send it to the Cantina, I would send it a goal through the action server with the pose in the Cantina I want it to go to, and it would start running. And while that's running, I can do other things. So actions are, unlike services, ways to do long-running things, but without the blocking aspect of that. The other thing that makes them very useful is that they're preemptible. So if I get halfway to the Cantina and I see a fire off on the left, my system, I would cancel the action to drive to the Cantina and then hopefully go and fight the fire, with my awesome fire fighting robot.
Gavin, it's Peter.
Yes.
The progress messages you get back from the action, do you have to poll it, or does it just stream them to you?
It just streams them. So when I run the action server for the demo, I'll show what it does is when you create an action server, it creates like 6 different topics. And then you can listen to those topics and you'll get information like, the feedback, or you can just say, here's my goal. I don't care what you're doing. Just tell me when you're done. But it's basically, it will just start firing feedback and you can choose to ignore it or use it. Actually, come to think of it, I didn't show my service example real quick, so I'll just pull that up. It's very good, services. All right, the same thing as with publishers and subscribers, you just import ROS1, except with this, instead of using just a single message, you now have the concept of your type and response and request messages as well. It's not the nicest system they've come up with, but it works. The same thing, you initialize a node, except in this, you're not creating a publisher or a subscriber, you're creating a service. You give it a type and a callback. Then in your callback, you do stuff with the data that you got. Then you send a response back to the client. And the client is pretty much the same thing. Initialize a node, create a proxy to my service, client. We wait for it to come up. So basically what can happen is I can create a service and then I can send a message, but the service might not actually exist at the other end, and then my system will crash. So generally the standard approach is you create your client and then you wait for the service to actually exist. So you do this in the setup of your process. And then all I do is I'm basically just sending requests to my service and then printing the response and flipping my flag. It's all very straightforward. All right, now to actions, the joy. Okay, so ROS1, my action server. Oh no. All right, so on the left, I have an action server. So that will be the thing that will actually execute the task I want. And on the right, I have an action client, and that's the thing that will send the goal to the server and then wait for the client to, the server to respond back that it's done. For context, the server I've implemented, basically you send it a number of steps you want. You assume it's a walking agent. I want you to walk 20 steps. And there's a bit of non-determinism whether or not the agent will fall down. So there's a 10% chance or 5% chance that the agent will fall down. So you can see here that the agent is taking steps. Ignore the step count thing, that was some debugging I had. And the agent happily took the 20 steps. So you see there that doesn't want to fall over. Was really happy to fall. Oh, there we go. I fell down, and my action concludes at that point. So I can also send conflicting goals, and it will preempt and cancel my previous action. But there's a lot of flexibility with this, and we use this for, like I said, things like mobile robots or mobile manipulators, where we tell the arm, I want you to move from here to here. And we want to be able to stop it if it collides with something or some other kind of event like that happens, or it gets a new goal. Action servers in ROS1 are a bit grottier. Basically, the easiest thing to do is actually to just wrap them in a class. So I have my class here called my action server. Oh, and as I was saying, actions aren't part of the generic ROS library. They're in this thing called ActionLib, which was this afterthought library they created. But here I create something called a simple action server. So this is just, oh my God, don't watch that screen. Simple action server. I give it an action type, an execute fallback, and then this auto start flag, which for good practice is generally set to false. I'm not going to go into why. But then we immediately start it, which makes the false flag kind of redundant, but let's move on, who cares. The main thing is I have this execution callback that when my action server receives a goal from a client, it will start executing. And in this case, it's basically just this task of having the agent take n number of steps and then publishing feedback as it goes. So every time step, it will publish that it's taken an extra step with a 5% chance of falling down. If it falls down, I set the thing to aborted. If it succeeds, however, I can set it to succeeded. So basically, there is a state machine running underneath the hood here that you do need to manage. If you don't manage it, you'll get lots of annoying warnings and errors saying that your action server's kind of buggered. And it's just a case of, again, kind of instantiating this action server and then going into this kind of wait spin thing down the bottom. My action client is even simpler. I create a node. I don't even bother putting it in a main function. That's how simple it is. I create an action client for my walk action. I wait for it to be available. And then I send it a goal of walking 20 steps. And I wait for that goal to conclude. And then I print the result. So it's quite flexible in that regard. And I can do things like, instead of waiting for the result, I can, wait 20 seconds or 10 seconds. And then I can cancel all goals. So I can actually say, I don't want to do this anymore. Let's move on. Okay, so that's publishers, subscribers, services, and actions. They're the main three components of ROS. Everything else is kind of just nice to have around the side. One last thing before I move on to ROS2 is in ROS1, they do have a concept of multiple nodes per process, but I'm going to air quote that because it's this basically this thing they tacked on towards the end called nodelets, which you basically have to build as shared objects and then you load them dynamically at runtime. But one thing they do give you compared to just having one node per process is if you're doing really memory intensive operations, like you're dealing with point clouds or images, you don't necessarily want to keep serializing them and shoving them through sockets. Sometimes it's better to just use shared memory. So nodelets give you this option to use this kind of shared memory pool, but they do decrease fault tolerance. So if one thing goes down, the whole thing kind of goes down. Right. So just a last little thing on ROS1, actually, sorry, is this discovery thing. So how does discovery work? Well, I talked about initially this idea of the ROS master. I had to turn my ROS master on before I could run my first publisher. The ROS master is basically this thing that exists on the side that when a node comes online, it communicates to say, I'm interested in publishing these topics. I'm interested in subscribing to these topics. So when another node comes online that is also interested in these, tell them, here's the port number I want you to communicate with. So the same situation here. And then they will start listening, talking to each other. And at this point, they're no longer communicating with the ROS master. Now, one issue with this is you can end up in a situation where you have what are called orphan nodes, where you start a node up, it communicates to the ROS master, and then for whatever reason, the ROS master dies. The publisher will not shut down generally. It will still continue to exist, and it will wait for incoming connections that will never come because the ROS master that knew about it is now dead. So just to demonstrate that, go back to my publisher subscriber. So these are still publishing. If I go to my ROS core and I kill it, these are still publishing and talking to each other, but nothing else can join this conversation now. So that is an infuriating problem with ROS1. Another issue with this is that all the nodes have to know where the master is. So if you have ROS split over multiple machines, the location of the ROS master has to be addressable by every machine on the network. All right, So moving on to ROS2 now. So in ROS1, the way that your system is set up is you have your user code. It communicates to the middleware, which serializes all of your messages, shoves them through the network stack to another middleware, which then decodes them and passes that back to user code again. Right? In ROS2, they have used a third-party off-the-shelf middleware called DDS. So they've given up on this idea of maintaining their own middleware. But what this means now is your user code will communicate to a ROS client library, which will then communicate to the ROS middleware, which will do the serialization, etc., and pass through the network stack back down the chain. Now, one of the reasons they've done this and one of the advantages of this is A, they're not maintaining this code themselves anymore. There's also a lot of off-the-shelf DDS platforms implementations available because DDS is a specification, but it also means that they can interact with software that is not necessarily written in ROS. So you can send messages to other systems, not just ROS systems, as long as they're connected using DDS. Why use DDS? I love this. This was from their design page where they listed all the things that use DDS, and I love that the first thing they said there was battleships. They could have said Navy vessels, but battleships. As well as a bunch of other things like space systems and train switchboards, etc. So there's a lot of pre-existing hardware and software out there that takes advantage of this, and so they're trying to leverage ROS into these ecosystems as well. So that's part of the rationale for that. One nice thing about the choice of DDS is that there is no longer a ROS master. So DDS uses magic. I'm going to call it magic. When a DDS node comes up and another DDS nodes come up, they will find each other independently over the network without needing to have a single service in the middle that helps them facilitate that communication. So what I'll do is I'm going to now kill all of these just to shut them up. And I'm going to go over to my other trusty terminal. And I'm going to start a talker and listener in ROS2, but I haven't started a ROS master. So that increases, that decreases that increases the fault tolerance of the system because it means you're now not dependent on this one point of failure. I will come back to those in a moment. But so another thing with ROS2 is they have moved on from Python 2.7 finally, thank the Lord. They are now using Python 3.6 as a minimum and C++. And one of the great things is under the hood, it's actually a shared C implementation. So both languages effectively operate in the same way. So it's predictable what's going to happen when you move from Python to C++ and back. And they refer to these libraries that are written on top of their shared C implementation as ROS client libraries. So you have RCL Pi and RCL CPP, for instance. And now going back to my publisher subscriber thing, ROS2 nodes now look more like nodelets. So in ROS, you have a single node per process. In ROS2, you can have multiple nodes per process. This does change things a little bit. For instance, in Python, subscribers are no longer done in threads. So ROS2 code becomes somewhat blocking. So let me just pull up my talker. So I have a listener and I have a talker. In my listener, I import this RCL Pi thing, ROS client library for Python, and I also import from that this node class. And all of my nodes that I'm going to develop will inherit from this node class. So I have an initializer in there where I give it a name, and then I can create from that subscribers on topics. I can create services and publishers and everything else. So in this case, I've got a subscriber with a listener callback. It's very bare bones. Down in my main function, I still have to initialize the client library, but it's not the same as initializing the node. It's a bit of a different way to think about it. The node initialization now happens in the class. I create an instance of that class. Then in order to get messages, so as I was saying, it's no longer multi-threaded. In order to get messages, you actually have to use the spin functions that are available both in C++ and Python. When I call spin, it basically will go and take the node and check if messages have arrived on the message queue for the various callbacks in that node. This is only going to work obviously for one node here, because spin will basically block until I hit Control-C, but they have now finally added to Python spin once, which was always a thing in C++, but was never a thing in Python. But what that lets me do is listen for messages, just listen for messages if they're here now. Otherwise, I can do something like publish some other messages. So I can mix subscribers and publishers together in the same node. Then just some shutdown at the bottom, right? Nothing too complicated. The same thing with a publisher. It's just another node class. I create a publisher. And one other thing I can do here is I can create events. So I can create timers that I can attach to my class that basically when my node is being spun, when they wake up, the resulting callbacks will be called. So in this case, I've created a timer at 1 Hertz, which we'll call my timer callback, which will then just publish my string message to my listener. So that's all that is needed to get these two nodes communicating with each other. Now, one thing that I think is really fancy about ROS2 is the fact that you can actually merge nodes into a single process. So in this file here, I'm importing my publisher and my subscriber from the other two files I showed you. I'm instantiating each of those nodes, and then I'm creating what's called an executor. So when you call ROS rclpi.spin, it uses its own executor under the hood you don't know about, but you can also create them yourself manually. What this lets us do is we can then add nodes to our executor and spin that, and it will now check one after the other if both nodes have messages in the queue ready to process. So it gives you a lot of flexibility. You can create quite complex systems, and in C++, if you use things like unique pointers, etc., you can now get away with having nodes that all operate on the same image, but without any memory copying at all, which should speed things up. There's no serialization anymore. It should be a lot faster. Okay.
Is that only in C++ or in Python as well, the memory sharing?
So it is probably only in C++, just because Python has its own weird inherent types underneath. It might not be, though. It might be both, because it is the data is in C land. So it's worth a look, actually. The next thing, this is a weird thing about ROS2. If you've never written asynchronous code before, this is going to maybe break your brain a little bit. But services in ROS2 are now asynchronous, and they return something called a future. They don't return the result of your request as they did in ROS1. Now, futures are things that you can poll and cancel. So when I say poll, I mean you can look at it and say, are you done yet? Are you done yet? Are you done yet? Ad nauseum until it finishes. This lets you basically kind of move on with other computations you might want to do, while still knowing that at some point you'll get the result of your service. You can also attach callbacks to your futures once you've got them, so that when your future resolves, the callback will get invoked and it will do some extra processing from there. But I have in big bold font down the bottom, if you use services incorrectly in ROS2, you will get deadlocks. And the way they've implemented that is a little bit bizarre. I have here my fun little ROS service I'll show you just for the sake of completeness. But basically, it's just an addition service. I run that. My service over on the side tells me what the request was, and then I get the result on the right, left and right, sorry. And if we go and look at services, and I'll talk about how you get deadlocks, etc. as well. So the service is pretty straightforward. I create a node. I create a node class, I create a service within that class, and I have a callback. So I don't want to go too much into that. It's pretty much the same thing. Down here, I spin that node, so it'll start checking for messages from clients. Now the client is where things get a little bit different. So I have a client node. I create a client to my service, and I wait for it to become available. This is arbitrary. One nice thing in ROS2 I'll just point out is that in ROS1, when you generated service messages, it would create things like add to ints request as one big word, all in camel case. In ROS2, they've modularized everything. So it's now a lot more clear what the hell is actually happening. My request is just going to read from standard arguments, and it's going to call asynchronously my client, my service, sorry. Now, what this will give me back is a future, which I can then spin until it's completed. So basically what I'm saying here is keep checking my node until my future says it's done. So this allows me to basically stop execution and block there, and then carry on once it's resolved. You can also do this just with a simple while loop. So you do something like is done, while not done, etc. Just keep spinning once. Now, where things can get a little bit dicey is if you chuck off the async here. This is a valid call. Ow, my knee hurts. The problem is call is actually blocking, and what it will do is it will wait for the response to come back from the server. Now, if I don't spin, I will never know that I got a response from the server. So at this point, I'm stuck here. I'll never hit my spin here, and I will never get a result. So now my client is effectively stuck forever. So let's just demonstrate that. So what have I done here? Oh, yes. So one annoying, and I say annoying, I mean immensely annoying thing with ROS2 is in ROS1, when you change your Python files, you don't have to rebuild everything. In ROS2, you do actually have to rebuild everything.
Yeah, but there's a -- symlink install or something like that.
Oh, fantastic. I had actually seen that, and then I completely blazed past it. So thank you. You've changed my life. All right, so if I now run this, you can see that the server got the request, but the client will never actually return. And it's now basically stuck in this wait loop. So the way around this is either to just use the async call or to actually spin your call itself off into a thread. But it's an up to you type situation.
Gavin, just so you know, you're at 12.
Yes, so if people need to leave, feel free. I'm almost done, but if you need to leave, that's fine. Action services are now part of the core library, and they're implemented using a mixture of services and publishers instead of just publishers. There is real-time support in ROS2, so that was always apparently a big gripe with certain systems. If you needed real-time support, it was not natively supported by ROS. You couldn't guarantee real-time accuracy of things. For some people, they'll be happy. I'm grossed out. There's also Windows support with SadFace. There is a lot more to ROS2 than that, but I just wanted to give you a basic overview, and obviously time was a factor with this talk. But other than that, thank you very much. And any questions or comments or discussion?
I've had one thing, so I attended ROSCON last year and in 2019. This is James, by the way. And I think one of the really nice features in terms of simple usage was the quality of service features available in ROS2 for subscribers and publishers. I put a little link in the chat. So basically you can do things like have deadlines, so how often you need to be sending a message, else it'll throw out an error. So it makes it a little bit more safe in those safety critical aspects, which I know not everyone necessarily deals with. But it can just help maybe make sure that your data is in and your sensors are acting accordingly. and things like if you haven't received a message in X amount of time, throw out an error and things like that.
Yeah. So I got a question from Fabio. Can you comment on ROS2 and ROS1 and how they can interact, or do I need to port all my code? So that's a very good question. They have developed a thing called ROS1 bridge, and what that lets you do is effectively pass messages between ROS1 and ROS2. So you can have nodes in both ecosystems. In ROS1, you still do have to have a master, but they can be co-located on the same machine. One caveat with that is that the ROS1 bridge does not support action messages at all. So if you have action servers that exist on either side of that, they will not be able to communicate over the bridge.
And depending on your message type, you may need to do a little bit of tweaking on either side to do like a custom message or something like that. Again, there was a ROSCON 2019 talk on it. And there should be videos to all the ROSCON talks from last year, so somewhere.
So I played with exactly what James is talking about. One thing with the ROS1 bridge is it's all implemented in C++. Anytime you add a new message definition, you need to recompile the bridge. And that seems fine, except for the fact that compiling the bridge takes 20 minutes.
Kevin,
So,
did you want to talk a little bit about what the intended way forward is with ROS1 and ROS2 from what our current sort of thinking process?
Yeah. So at present, we have a lot of resources in ROS1 land, which has allowed fast development on a lot of our platforms, for instance, the Panda ARM. The goal moving forward is we can't stand Python 2 anymore. That is not a thing. There is one last release of ROS1 called ROS Noetic that does only support Python 3. It's the first ROS implementation that is natively Python 3 only, but it is also meant to be the last ROS1 release. So we can upgrade our stuff to Python 3 and stick with ROS1, but then after 2 more years, we're kind of dead in the water, or we can start now porting our stuff over to ROS2. I think for things that are mission critical, like I said, action servers that we need to run the robots, it's probably worth porting them now. Things that rely on, for instance, image messages, so your camera and your camera processing nodes, if they're already in ROS1, they could probably stay in ROS1, and you could use the bridge to facilitate the communication between the two systems. So I think all of our action stuff needs to probably go to ROS2. Stuff that doesn't require actions can stay in ROS1 for now until it's feasible for people to bring them over. Is ROS2 friendly with Conda? You talked to me about this earlier.
Yes, yeah. So I was actually about to put an interesting thing slide up in maybe next week or a couple of weeks' time. In general, there's been a lot of work on ROS1 and 2 with Conda. So Conda is like a Python, mainly Python package manager, which has now kind of exploded and included more packages around it. So ROS1 and 2 is kind of supported now with a couple of caveats with quite a few bugs and stuff. But yes, there will be ROS1 and 2 in Conda, or is already. So if you want to play around with it, I will put an interesting thing slide on.
So Fernando asked, how do you set up multiple machines in ROS2 since there's no ROS master? I have yet to figure it out. I tried it this morning and I couldn't get it to work. So that'll be a bit more poking. Have you seen anything with that? The answer is not too sure at the moment, because most of my playing around has been on my same machine. I did set up a node on my laptop, which is on the Wi-Fi, and my desktop, and they couldn't find each other. But I do believe that if they're on the same subnet, they should be able to communicate with each other.
So then how do you deal with independent?
Yes. So they have this thing called a ROS group ID that you can insert it's a environment variable. When you start your nodes, this ROS group ID gets read, and then it will only communicate to other nodes that have the exact same group ID. So you can have some security with that, but it's a bit scary at the same time. I don't know if someone sitting over in G block could ROS topic list and potentially get access to all of my ROS stuff if they're on the same subnet. I need to find a bit more on that, sorry. Do you still have to do nested XML launch files in ROS2? They have the option for nested XML launch files. They've completely changed the syntax, which means if you have launch files in ROS1, you have to rewrite them in ROS2. But the other thing that they're more pushing on is they have a Python API for launching resources now. They had it in ROS1, but apparently there was like zero documentation, so no one used it. In ROS2, they now have a Python launch system, and supposedly you can do ordering constraints and dependencies between your nodes.
So do you really think that in 2 years' time, there's not going to be any ROS1 support anymore, considering that there's thousands of packages and thousands of users and community driven?
Yes, that's a fun question. Most of the third-party packages that we use are now basically on like end-of-life support. So, for instance, one thing that Ben and I use quite heavily, like PyTrees are basically exclusively targeted at ROS2 now, and it's very much like this is the problem with Python 2.7 and Python 3. Stuff is still supported with ROS1, but they're kind of starting to jump ship to ROS2, and backporting fixes is needed. Yeah, I think it would probably be better to start new projects in ROS2. So Frederick asked, would I advise ROS2 or ROS1? I think new projects for two reasons. One, for future-proofing, and also two, for upskilling. There's no point learning how to use ROS1 now if the intention is for us to move to ROS2. And it's good that more people learn how to use ROS2 than not. So that's
Just to talk a little.
In terms of the community, for example, third-party open source for packages for Slam, for example, like they release it for ROS1. So how is it in ROS2? Is there a big development there?
Yeah, so actually, if you go and you look at the ROS index, they've got a new website now, the ROS index pages and all that, that basically list all the packages that are in ROS2. And a huge chunk of packages are now in ROS2. So, okay. I mean, if it's something that was developed by a PhD student back in 2016 and they've now graduated and they were the only maintainer, it might need to be ported over. But if it's actively maintained, then the likelihood is that they now have a ROS2 implementation. Steve, do you have a question?
I was just going to say that, like, as far as ROS1 versus ROS2 and everybody moving to ROS2, the main limiting factor is that there is nothing in ROS1 that exists now will work without modifications in a few years, because Python 2 is already a limiting factor for a lot of projects and a lot of things we do. Everything in like the deep learning community there's need for support for Python 3. And that really breaks a lot of things when you're trying to run ROS2 and ROS3 nodes with ROS1. So I think as much as there will still be ROS1 nodes that float around, I don't think there's going to be much of an option in the next couple of years to move away from 1604 and all of the stuff that currently is supported in ROS.
Yeah. And I'm just going to quickly go back to Fernando's question about the SLAM packages. Because they are not action servers, you can still use that package in ROS2 if you use the ROS bridge. Any other questions?
If not, we may just leave it there. Gone a little bit over time, but we're good. No more overtime than we've done in the past. All right.
So, a lot of information there.
And yeah, the other thing is, if you're interested in ROS2, go check out some of the ROSCON talks from like past couple of years. There's always been a lot of ROS2 stuff in the past couple of years. They're not always great, I'll give you that, but there are a few good ones. So yeah. Sorry to interrupt there, David.
No, that's all right. I'd also just sort of say that if anyone is working on ROS2 stuff or starts working ROS2 stuff, make sure you're talking to the engineers and all that, so that we as a unit can start to come together and in this transition from ROS1 to ROS2. So everyone, let's thank Gavin for the very informative talk with hand claps.
Toby has a.
Whoop.
Oh, thank you.
One more question. How stable is ROS2? To say release new versions, it feels like every fortnight.
Yeah. So they base in every year. You get bugs. So like the thing is, the first time I heard about ROS2 was when I been talked about forever. As long as ROS similar. So I mean, it's stable, but obviously there's still teething pains, and I think a lot of that is to do with the fact that a lot of there's still going to be a bit of force to push the community over to ROS2, and that's when a lot of these things will start to be fixed more rapidly. I think the basics are there, sufficiently there for it to be workable for us now. Sorry, David.
No. I was basically done with the applause. All right, thank you very much everyone for coming.
I want a second applause now.
Okay, second applause. Needy. Thanks everyone for coming, and stay tuned for more technical talks. There should be one at the beginning of every month.